Alright, in this video we're going to look at the differentiability and local linearity lesson. Specifically, we're going to talk about types of non-differentiability and some of the implications of differentiability and non-differentiability. So the first thing we're going to do is look at the various types of non-differentiabilities that can occur. The first is a corner. And here are the salient characteristics of when we have a corner. We have one-sided derivatives that are different, and they're finite. So for instance, maybe the limit as x approaches 2 of the derivative from the left is -2, and the limit as x approaches -2 from the right the derivative is 1/2. So what that means is if I'm just going to put a generic point on here at x equals 2, but we have that the derivative is -2 to the left of that, and so we're going to draw a segment, a line emanating away from there, where the slope is -2. And the limit as we approach it from the right is 1/2. So we draw a line right there. And what you see here, right here, where these two meet, is there's a corner. Two segments meeting at a hard corner. That's the first type of non-differentiability. Alright. The second kind of non-differentiability we might see is what's known as a cusp. Cusps happen when the slopes of the curve as you approach a point approach -infinity from one side and +infinity from the other. So let's say that the limit as x approaches 3 from the left of the derivative is -infinity, but the limit as x approaches 3 from the right of the derivative is +infinity. I put a point on the curve at x equals 3. Now the derivative as we approach it from the left is getting closer and closer to -infinity. It's real sharp like that, coming from that direction. And the limit as we approach it from the right of the derivative is +infinity, so it's coming out of here with an infinite slope. And what you see here is a cusp. It's known as a cusp. Alright. Third type of non-differentiability that can occur is a vertical tangent. Vertical tangents happen when the slopes of the curve on either side of the point both approach -infinity or both approach +infinity. So let's say that the limit as x approaches 1 from the left the derivative is +infinity, and the limit as x approaches 1 to the right of the derivative is +infinity. Okay, if we put this point on here at 1, the derivative is getting closer and closer to infinity as we approach this point, and also from the right hand side it's getting closer and closer to infinity. What happens here is we actually have a vertical tangent line to the curve. I'm just going to draw this dashed line in representing the tangent line to the curve there. And that line is vertical for an instant right here where x equals 1. That's a vertical tangent, another kind of non-differentiability. And a fourth kind of non-differentiability we might see is a discontinuity. And whenever we have any kind of discontinuity, a function is non-differentiable there. So I'm just going to draw one in here. Maybe you've got a jump discontinuity. That's an example of a place where that function is going to be non-differentiable. Alright? So those are the four major types of situations where a function is non-differentiable. In example 1, we're looking at finding where a function is non-differentiable, And when we do this, it's frequently helpful for us to think about what the function looks like graphically. We can also think about the limits in various locations, depending on the type of function. For this particular function, f of x equals the absolute value of x plus 5 minus 3, we should all be thinking absolute value, those are going to be V-shaped. And so the location of this non-differentiability we can see if we just think about a general absolute value graph. The point of non-differentiability is going to be at the vertex. And so it's enough for us to find the vertex in order to indicate where this function is non-differentiable. And that happens at x equals negative 5, or at the point negative 5, comma, negative 3. There is a corner, and it is non-differentiable there. Alright, carrying on to a few more examples. Example 2, we're going to determine if the function is differentiable at all values of x. Well, first of all, since this is a piecewise function, I'll consider each of the individual branches and think about, are there any places where either of these would be non-differentiable? Well, the left-hand branch at x squared plus 1 is a parabola. Parabolas are always smooth and differentiable, so this function is going to be differentiable at all of those values where x is less than 1. And to the right of 1, the function is linear, so it's going to be differentiable everywhere there. So where are we concerned with whether or not it's differentiable? We're concerned at x equals 1, where these two pieces meet. And so we're going to find the value of the derivative at x equals 1 for both of these pieces. And if they give us some kind of indication that they're not the same, then that means that the function is non-differentiable there. So first I'm going to find the derivative of x squared plus 1 at x equals 1. So we've got the limit as h goes to 0 of x squared plus 1 f of x plus h minus f of x all over h. And we find this, and that's x squared plus 2xh plus h squared plus 1 minus x squared minus 1 all over h. Some things that cancel out here, the x squared plus 1 and the minus 1. I'm just going to go ahead and factor my h a while. This is the limit as h goes to 0 of h times 2x plus h all over h. The h's cancel. And so this is the limit as h goes to 0 of 2x plus h is equal to 2x. And so the value of this derivative at 1 is 2 times 1, or 2. So that's my left-hand derivative. My right-hand derivative, I'm going to handle in a similar fashion. We take the limit as h goes to 0 of 2 times the quantity x plus h minus 2x all over h. So that's equal to the limit of h goes to 0 of 2x plus 2h minus 2x all over h. Got some things that cancel. This turns into the limit of h goes to 0 of 2h over h, which is just the limit of h goes to 0 of 2, which is 2. And so, since the derivative from the left hand and the right hand side are equal at that crucial point, we've now determined, yes, this function is differentiable. Come on, then. Yes, it is differentiable. Okay. Some of the implications of differentiability are listed here. Differentiability implies local linearity. Differentiability implies continuity in the intermediate value theorem. We're going to come back and do one more video to talk about these implications of differentiability and then look at example 3. So check back in for that video, and we'll see you next time.